I saw there's another question on the back seat. Well, you can ask a question in the panel discussion. All right, cool. The next paper is SkinLink, Unbounded Construction and Prototyping of Reconfigurable Epidermal Interfaces. The presenter is Ping-Sun Ku from Cornell University. He mentioned that he is looking for a summer internship next year in sensing and wearables.
Thank you, Chen, for the introduction. So this is Ping-Sun, and today I'll be presenting our work, SkinLink. So SkinLink is a construction kit that supports prototyping wearable interfaces directly on the body. As illustrated in this example diagram, SkinLink comprises of the lightweight printed circuit modules and adaptive trace modules to support a reconfigurable on-body construction workflow. To give a brief background, fabrication methods for on-skin interfaces can be categorized into either off-body or on-body fabrication. So, off-body fabrication can create conformable, lightweight, and fully integrated on-skin circuitry. Components including substrate, electronics, adhesive, and art layers are produced separately and assembled before applying to the body. However, long hours of fabrication is required for the amount of details put into the designs. It is therefore challenging to iterate circuit designs through rapid prototyping. Alternatively, on-body fabrication offers faster fabrication time by printing or painting conductive materials directly on the body. Nonetheless, these approaches are often hindered by the thicker trace, and this leads to a more straightforward single functional design. Most importantly, previous fabrication methods do not support on-body modification of the device during or after fabrication. This is where we see design opportunities for prototyping tools with faster iteration time, on-body adjustments, and capable of integrating diverse functions. To fill this gap, we set our design goals of SkinLink system to provide an extensible modular circuit structure to enable flexible and stretchable circuit wiring and to support fast on-body prototyping. We designed various sensing and actuating modules to support a broad range of on-skin interactions. To reduce the back and forth design iteration, we want the circuit construction and modification to be done directly on the body. The slim and lightweight form factor of the modules allow users to easily attach and detach the device with a silicone glue. To make the circuit modules lightweight, we implemented a centralized system structure where every functional module links to the single microcontroller at the center through bus wires. As a proof of concept, we designed 14 modules, including sensing, computing, actuation, and communication functions. Here, a penny is shown for the scale reference. Supporting multiple communication protocols, engineers with knowledge of circuit design can extend the module library with new sensors and actuators. Another key implementation of SkinLink is the conductive traces that dynamically connect between the modules. Here we see the multi-layer structure of the wire made with core, conductor, and coating. So six copper wires were braided into one module to support the signal transmission of communication protocols. We found that depending on the core fiber, the wire modules differ in strength properties. For example, if the core fiber is elastic, the whole module will be able to elongate according to the stretch. So after experimenting with options of the core fiber materials and also the coating, we made 4 types of SkinLink traces with diverse properties, from rigid to stretchable, that are suitable for linking modules across different parts of the body. To further evaluate the usability of SkinLink, we conducted 2 user studies. In the first study, we invited users to experience 2 on-skin toolkits developed from our lab, SkinKit and SkinLink. By comparing the 2 approaches, we want to see how much we've improved in supporting on-skin circuit prototyping. So here's a brief introduction to SkinKit, the toolkit we compared. SkinKit has two main components: skin conformable substrates and reusable plug-and-play circuit modules. The magnetic modules are pre-programmed and must be connected in a particular sequence to work. For example, like power to sensor and to actuator. Besides, the wire module of SkinKit is made of conductive fabric tape on a non-stretchable substrate. 40 participants were recruited to learn the two toolkits and build an example on-skin device made of LEDs and IMUs. While limited to use modules of the same sensing and actuation functions, participants were tasked to explore the device shapes and the on-body placements independently. So the study result is analyzed based on the customized device and the user feedback. For quantitative result, participants spend less than 30 minutes on average fabricating the prototypes for both toolkits. However, participants used much less trace modules for SkinLink, and the prototype took up less skin area. Qualitative feedback shows SkinLink enables a more flexible wiring process, unrestricted circuit arrangement, and less interfering wearability when designing an on-skin prototype. This is how we visualize the improvements in the 3D space coordinated by the three criteria: ease of fabrication, circuit complexity, and reconfigurability. We conclude that SkinLink outperformed in the reconfigurability and circuit complexity, while the ease of fabrication stays similar to SkinKit. To explore the expressiveness of SkinLink in depth, we collaborated with artists and designers to create artistic on-body wearable projects. Interestingly, participants found that the prototyping process is similar to doing makeup, where iterative adjustment on the body is often necessary. Participants mentioned that it's impossible to reach the ideal design with the first attempt. Seeing the modification on the body provides direct feedback for quick adjustments. Here we show the participants utilize the toolkit to create expressive or concealed designs. So for this one, inspired by the social distancing regulation during the pandemic, the on-face prototype provides a vibration pulse feedback on the cheek when someone stands within 2 feet of the wearer. Another project conceals the entire device under a thin layer of prosthetic skin. So the 4 hidden LED can light up sequentially based on the proximity sensor on the back of the palm. And lastly, the Hybrid Body Lab Artist in Residence project also utilized SkinLink to create an auto headlight controlled by the ambient light intensity. As a personal anecdote, I was the one who created the toolkit and also the model wearing the design. So in a nutshell, SkinLink is an on-body fabrication approach for prototyping on-skin interfaces. We develop a customized construction kit with adaptive traces and diverse circuit modules. For more information, please refer to our paper. Thank you for listening.
Sorry, I think we can take one questions. Any question? Feel free to get the microphone there.
I'll ask a quick question. Thank you for the presentation. Did you do any, at least even, observations about how bodily fluids affect your system?
Thank you. That's a good question. So in our studies, we only have the participant to wear the device in like 10 minutes. So it's not long enough to observe those effects, like body fluid or body hairs. But we think that's the very critical things to consider if we want to deploy the device in a long-term situation.
All right, cool. Thank you, speaker again.